In this module, we will be looking at techniques for estimating best fit parameters for nonlinear models, or more correctly, models with normal equations that are nonlinear. Learning objectives for this module include being able to identify model formulations for which best fit parameters can be estimated using nonlinear regression, understanding basic concepts of how to estimate parameters for nonlinear models and pitfalls to be aware of, and being aware of some of the advantages and disadvantages of different algorithms for conducting nonlinear regression. Okay, let's get started. Previously, we've looked at models for which the normal equations are linear, and therefore we could find one and only one set of best fit parameters using a direct calculation procedure. Remember, the normal equations are systems of equations we get when we differentiate the model's error sum of squares function with respect to each model parameter we are trying to estimate. We are now going to consider the case where the normal equations are nonlinear. The overall approach will be similar to what we've done previously for linear regression. However, because the normal equations will be nonlinear in this case, and therefore generally not directly solvable, we will need to identify additional strategies for solving them. Two examples are shown that depict models with nonlinear normal equations. The first of these is intrinsically linear, meaning it is nonlinear but can be transformed, in this case by a log transform, to a linear form, and as a result, the transformed model parameters can be estimated using linear regression. The second equation is intrinsically nonlinear, meaning there is no transformation that will convert it to a linear form. In this case, we have no alternative other than nonlinear regression for estimating parameters for this model. To develop a nonlinear regression, we start with the same basic approach we took for linear regression. First, we determine an error function using the error sum of squares, just as we did in linear regression. Second, we differentiate the error function with respect to each model parameter we are trying to estimate and set these to 0, again, just as we did with linear regression. This allows us to generate the normal equations. However, for nonlinear models, the normal equations are nonlinear, which generally means two things. First, we will generally not be able to directly calculate the best fit parameters from the normal equations. Instead, we will need to develop iterative solution techniques. Second, there is no guarantee that a single best fit solution will exist. There may very well be multiple solutions that minimize error. Related to this latter point is the possible presence of local minima on the error surface. We will need to be very wary of these local minimum as they represent parameter sets that may result from a solution technique but may not be the best or global minimum of the error surface. Let's work through an example using a simple nonlinear model. Our response variable y is a function of time. Specifically, y is equal to e raised to the at power, where t is time and a is a model parameter, and in fact is our only model parameter. To conduct a nonlinear regression, we follow the same basic approach we took with linear regression. First, we determine the error function SR. Second, we differentiate this error function with respect to each model parameter, in this case, the single parameter a. We set the normal equation to 0 to find the minimum of the error surface, just as we did in linear regression. However, this normal equation is nonlinear, and we can't directly solve for a. We'll need to develop an iterative approach for determining the value of a. Additionally, we need to be aware that because the normal equation is nonlinear, multiple solutions may exist for a, each of which represents a local minimum. For this simple nonlinear model, we can utilize a straightforward algorithm, Newton's method, for finding roots of functions. To get started, we simply add a to both sides of the normal equation. This has the effect that, given an initial guess for a, we can plug this value into the right-hand side of the modified normal equations to calculate a new, updated value for a. We then apply this approach iteratively using an updated value of a in the right-hand side to estimate another updated value for a. This process is continued until a converges to a fixed value. That value will be a local minimum on the error surface. This approach, while straightforward, is not particularly robust. It is susceptible to local minima and is not readily adaptable to models with more than one parameter. We need some more robust parameter estimation techniques for most problems you are likely to encounter. As we have stated previously, for nonlinear models, we need to be concerned about the local minimum problem, but there are other issues we need to be aware of. As alluded to previously, for models with more numerous parameters to be fit, and therefore have higher dimensionality error surfaces, we need more robust methods for fitting these parameters. Second, with nonlinear models, we need to be aware that multiple best fit parameter values may exist, and at the very least, multiple local minima may exist. Finally, as the dimensionality of the error surface goes up, we will likely need more data to estimate parameters with confidence. So to summarize, nonlinear models have significant advantages over linear models in terms of representational power, since virtually any relationship can be modeled using a nonlinear function. However, at least in terms of estimating parameters, linear models have significant advantages as well. We can generally directly solve for the best fit parameters, and we can be guaranteed that the parameters we find will be optimal. Still, most models in ecological engineering, and in other disciplines as well, are nonlinear. So we need techniques that work for these models. Fortunately, computer algorithms are widely available for automating much of the task of doing nonlinear regressions. We will be looking at developing computer programs for solving these problems, but first, let's look at some of the more robust techniques for fitting parameters to nonlinear models. We will briefly look at three techniques for nonlinear regression that overcome one or more of the problems we've seen with nonlinear normal equations. The first of these, gradient descent, is a family of methods that are reasonably straightforward and generally perform well, but are susceptible to getting caught in local minima. The second of these is simulated annealing, a stochastic search method useful for overcoming the local minima problem. Third, we look at genetic algorithms, providing an approach that starts with a population of possible solutions that evolves to an optimal solution. And finally, if all else fails, it is common to hand-fit a model by taking best guesses of parameter values, assessing model performance using those values, and then manually adjusting as needed to achieve the desired level of model performance. This method can be tedious, error-prone, and time-consuming, but it is often used for very complex models. For example, models of watershed hydrology. Gradient descent methods refer to a family of similar techniques, all based on visualizing the error function as a hilly surface for which we are trying to find minima, or the bottom of the valleys in the function surface. We start at some initial point on the surface, representing the initial guess at the parameter values. We then calculate derivatives in each dimension, remembering that each dimension represents a model parameter. This derivative can be thought of as the slope of the error function at that point in the direction of that parameter's dimension in error space. By evaluating each slope, the direction that is most downward can be determined by taking the vector of the downward slopes. Let's look at the case of the model with a single parameter a, and therefore an error function with a single dimension. We would start gradient descent by taking an initial guess for the value of a, as shown on the chart. Next, we calculate derivatives of the error function with respect to the parameters, a single one in this case, to determine which direction is downward on the error surface. We take a step in that direction. How large a step is generally a function of the steepness of the surface. We can take larger steps when the surface is steep, and smaller steps when the surface is not steep. We repeat this process until the slope is reduced to zero. At that point, we will have found a minima on the error surface. Gradient descent techniques generally work well, but can get trapped in local minima. Generally, this is not a problem with well-behaved models with small numbers of parameters on the order of, say, 2 to 5, but it is something to pay attention to. For more complex models, we will need strategies to avoid getting stuck in local minima. One way to avoid getting trapped in a local minima is to apply gradient descent, but use multiple starting points as depicted on this figure. The best, or global minimum, will be the minima that has the smallest error sum of squares values across all local minima identified. In this case, initial guesses of parameter values should cover reasonable ranges of the parameters in the model. This method generally works well but can be computationally expensive since in effect many individual regressions must be run, and the best regression solutions must be determined by examining these runs. One approach to addressing the local minima problem is to add stochasticity or randomness to the search process. Simulated annealing is one approach that does this. It is based on the idea of physically annealing metal. The idea is that when annealing metal, a process that makes it harder, you start with very hot metal in a highly excited state, and you slowly cool the metal over time. The slow cooling process allows the metal to relax into a highly ordered, low energy state. To apply this metaphor to simulated annealing, we start the system at a high energy state, meaning at a location, generally randomly selected, that corresponds to a high value of error. At this high energy state, rather than always go downhill, we add randomness to the direction and distance that we move, allowing us to sometimes jump across the local minimum on the error surface into another basin. As the algorithm proceeds, we cool the system, meaning we slowly reduce the level of randomness associated with each step. The idea is that initially, we want to fairly aggressively search the error surface for large basins of attraction, but after we have found these, we want to focus more on finding the minimums of that basin. Generally, this approach is effective for complex error surfaces with multiple local minimum and is more efficient than brute force gradient descent based techniques. A third class of solutions for nonlinear regressions are genetic algorithms. These are population-based solutions that take advantage of the genetic operations of recombination, selection, and mutation to evolve optimal solutions from an initial guess. The basic idea is to create a population of individuals representing distinct solutions to their problems, in this case, distinct combinations of parameter values. These parameter values are encoded in genes where each gene codes for one parameter. So for example, if we had a model with 3 parameters, A0, A1, and A2, each individual would consist of 3 genes, one containing a value for A1, one for A2, and another one for A3. Different individuals in the initial population would have a different parameter value encoded in their genes. The initial population is generated randomly. Once we have a population of solutions, we start the evolutionary process. Central to this is the concept of fitness. A given individual is more fit if it produces low error sum of square values and less fit if it produces high error sum of square values. The basic step of a genetic algorithm, then, is first, start with an initial random parent population of possible solutions. Then, let the population reproduce by randomly splitting and recombining genetic material, a process called recombination, to generate a new population of children solutions that represent various combinations of the parent population genetic material. Next, apply the mutation operator to each child. This operator randomly and at low frequency changes a gene's value. This introduces a new parameter possibility into the genetic material of the population. Finally, we evaluate each child's fitness by computing the error sum of squares for the parameter values stored in that child's genes. We then select the children that will take part in the next generation, biasing the selection process based on fitness. A child that is very fit has a higher chance of being selected for the next cycle, while a low fitness child would likely not be carried forward to the next generation. This process is repeated through multiple generations, with children replacing parents in each successive generation. Genetic algorithms tend to find high-quality solutions very quickly, often after just a few generations. Because they are population-based algorithms, they generally avoid finding local minimum because they are simultaneously searching a large portion of the parameter space, especially early on when the population is largely random. As the algorithms cycle through generations, the individuals in the population tend to converge on an optimal solution. This approach has been used successfully on a large class of model parameterization problems and is particularly appropriate if error surfaces are very complex or contain numerous local minimum. So, to recap, in this module we explored some concepts and techniques associated with nonlinear regression. First, nonlinear regression techniques are useful for fitting model parameters for models that have normal equations that are nonlinear. Nonlinear normal equations imply that a direct solution for best fit parameters is not possible and will require an iterative algorithm. Second, nonlinear regression can be susceptible to the local minimum problem, and multiple possible best fit parameter sets may exist. Being aware of the possibility of finding a local rather than a global minimum is essential when interpreting nonlinear regression results. Third, gradient descent techniques, while relatively simple, have downsides. They can be slow to converge and can get stuck in local minimum, but are still appropriate for well-behaved models with low numbers of parameters to be estimated. Finally, we reviewed simulated annealing and genetic algorithms as two approaches that can overcome the local minimum problem. Simulated annealing does this by adding randomness to the search process initially and reducing this through time, while genetic algorithms do so by taking a population-based approach that simultaneously searches large regions of parameter space using an evolutionary approach. We will be discussing programming approaches for automating nonlinear regression in an upcoming section of this course.